Okay. Hello, everyone. I think there are folks online as well. Hi to them. And I am Smriti Desai. I am the Software Engineering Director at Google, responsible for delivering storage systems, building and developing them. And I'm here with my colleague, Chris. Do you want to introduce yourself?
Yeah, I'm Chris Sable. I'm a SSD architect at Google.
Yeah, okay.
Software background.
Yeah, so we are probably, it's the last day of the summit and maybe the last but one presentation. So thank you for hanging out here with us. We promise we probably saved the best for last here. So moving on, today we're going to talk about SmartFTL SSDs. There is a popular anecdote.
We're on the intro slide still.
Oh, still? Why didn't it go? Okay, there it is. There is a popular anecdote within Google. What do we call an exabyte of free space at Google? Any guesses? It's an emergency low disk space situation for us. So, and what that means is storage is growing exponentially at Google. We continue to grow. And probably a few years ago, a petabyte would be a low disk space situation. And we are already at exabyte. We have several products with over 1 billion users each, presenting a breadth of use cases for the storage systems that we build at Google. We optimize for the storage total cost of ownership, TCO, and the key dimensions are, some of the key dimensions are the dollar per gigabyte and the IOPS per gigabyte, right? And we use both HDD and SSD-based storage systems, but today we'll focus on SSDs at Google. So at the OCP Summit, this is the first time ever we Google are presenting about SSDs. And specifically, we will be introducing the concept of SmartFTL. In this talk, we will share our learnings over the years, highlighting the trade-offs, architectural trade-offs of performance versus reliability versus garbage collection trade-offs in designing an SSD. In particular, we'll also talk about certain interfaces that we'd like to share with you and get your feedback on addressing these architectural points. And Chris will go deep into that. So Google has been developing SSDs since 2010, right? So we have had a decade of experience. We know how these drives operate in our data centers for the myriad of use cases. We have in-depth knowledge of the detailed drive design and its operations. So we started with the memory offload use case with search. That's how it was a simple PCIe SSD. Think instant search, and they needed a DRAM offload, and SSD was born for us. At that time, the host software did most of the job, right? Maintaining the flash translation layer, keeping the mapping table, all of that. Progressively, the SSD design, we incrementally started offloading to the drive. Over the years, DRAM was added to the drive, mapping table shifted to the drive. While we were doing this, we have been paying close attention to the industry, and we've been watching the NVMe marketplace. We are here because we do believe we can benefit from the industry optimizations. And we'd like to actually present what we think is a gap in the current NVMe SSD and how we are proposing to close it. And that is with respect to garbage collection efficiency. And Chris is going to talk all about it.
Thanks. So before we get into the details of SmartFTL and garbage collection efficiency, I just wanted to continue a little bit more trends. So I think Smriti touched on the host offload trend that as functionality has been moving to the drives over the years within Google. In particular, there's two kind of big examples. One is kernel bypass. So for a fairly long time, we've had applications talking directly to the SSD, bypassing the kernel layer, especially earlier for reads and for writes now as well. The other one is obviously, we started with that very simple drive that had the FTL on the host, and that's been pushed to the drive. Another big trend we've seen is the growing complexity of NAND. So with ECC, there's this transition from BCH to LDPC. LDPC has all sorts of knobs and tuning and complexity that needs to be dealt with. The 3D NAND transition has added layers and effects at boundaries between layers and things that must be dealt with within the SSD. And then there's also bifurcation between charge trap and floating gate out there as well. So that all adds to the complexity of the NAND space. On the positive side, performance continues to scale with SSDs, at least as far as we've seen. So there's plane growth to offset the growing die density. Independent plane read is a great thing that we've taken advantage of to maintain IOPS density. And program suspend is been wonderful for read tail latency. So kind of at a very top level, kind of our assessment of where industry is, most SSDs would have RAID across dies for error reduction. If you look at the NVMe command set, it's really focused around just read write, and there's a trim operation obviously for SSDs, but but the history is there with kind of the hard drive history on the command set. And then I would argue that they've historically been optimized for single workload. So that kind of works for Google use cases and kind of doesn't, right? So within Google, we kind of have two big use cases. One is what we consider local SSD. These use cases need very low error rates. The standard interface and standards-based functionality is critical, and they tend to have lower parallelism needs. So it's actually a really good fit for an NVMe, a standard drive available in industry. On top of that, we have a cluster file system use case, and in this use case, it's not as great a fit. We need data positioning control, right, which is sort of RAID precludes that to a large extent. The legacy command interface kind of precludes hints, and deeper integration with the workload for GC optimization. And the workloads tend to be highly parallel. We tend to have all the workloads running in a cluster, kind of hitting the drives in that cluster in parallel. Okay, so why does garbage collection optimization matter? Write amplification is a function of the workload and the flash over provisioning in the drive. And it's basically a measure of how much extra work you do for garbage collection. You probably all know this, I'm just level setting. So, so if you have a WAF of 2.5, it means for every 1 megabyte you write, the drive internally has to garbage collect, so read and write another 1.5 megabytes of data. So if you can reduce this, if you can go from a WAF of, say, 2.5 to 1.25, there's a lot of quantifiable benefits there, right? You can take that reduced WAF and then reduce the over-provisioning on the drive and go back up to the original WAF and have more bytes, right? So you can essentially have a more useful or yield more usable bytes per drive. You can use that to deploy a larger capacity drive, right? So if performance is a limiting factor for going from a certain capacity point to a larger one, you can reduce write amplification, go to a larger drive, and now you're saving dollars per byte as well in power. If you're wearing out a drive, obviously you can reduce the write wear out. So. Or that could potentially let you transition to a newer technology like a QLC or something like that. So we see a lot of benefit to write amplification reduction. So let's get into SmartFTL. So there's been a number of initiatives to try and reduce write amplification over the years. And we sort of kind of at a very high level tried to kind of break this down and come up with an interface that's somewhat scalable. Or where the responsibility is sort of tied in with the area with most knowledge in that area. So in a stock kind of standard SSD, you'd have the SSD responsibility would include flash management, the deciding where data is actually put on the SSD, and all the garbage collection decisions. And in a SmartFTL architecture, I'm kind of proposing that the drive really should still be responsible for all flash management. That's where the detailed knowledge of the NAND media and all of the required functionality for managing the NAND is, but kind of proposing that the application has a much deeper knowledge of where data should be placed and what is correlated lifetimes, as well as potentially GC decisions. So at a very high level, the stack at Google that we're working on here, on the left-hand side, you kind of just have the standard Linux block device stack and NVMe driver with a drive. On the right is kind of what we are envisioning here. So we use SRIOV with VFIO, so we're not going through the block device stack in Linux. We're not going through the NVMe kernel driver for our I/O path, and that really lets us tightly integrate with the application. And the SmartFTL library is a layer there that we add on top of kind of SPDK and DPDK standard open source software to encapsulate the SmartFTL functionality on the host side. And then in addition to that, there's this set of extensions that are provided by the drive. And then we'll get into those in a second here. So focusing on that drive functionality. So the key of this is a positioning or placement I/O directive extension to NVMe, which on a write-by-write basis lets the host specify kind of where data is placed down to the die level in the drive. Unlike ZNS, the data is still addressed by, in addition, data is still addressed by LBA. So you're tagging a write with both where it's supposed to go, but also the LBA. And that means that when you come back to read it, you just read, the read path is unmodified. It works like it would normally work. In addition to kind of this basic positioning functionality, there's two modes kind of built on top of this. One's a pure positioning mode, which is really just laying out data initially when it's written. There's another mode we call host managed GC or host GC mode, where the application can actually make decisions on what's garbage collected and where it's placed and when that happens. All these modes could exist with stock NVMe functionality. You could imagine it being something that happens in a SmartFTL specific namespace, while other namespaces could coexist. So before we run out of time, this slide kind of gets to the performance profile and why we see this as being one of the key value points we see of something like SmartFTL. What you've got here, core to this is the point I made earlier about RAID, right? If you have RAID, it implies a very rigid layout. If you can get away with that and place data, have control over it down to the die level on data placement, you can choose how wide to stripe it, right? So if in a normal SSD, I would just be striping data across all the dies in the drive. And that gives you full performance on any data you read or write. But it comes with a cost. On the left-hand side here, this is a simulated 32 megabyte random workload with different curves for different drive over provisioning operation points. So for example, right, if you're out of 128 dies in this hypothetical drive, with an OP of 25%, you get that yellow curve, right, which at 128 die stripe width gives you a WAF of 2.7. Well, if you can write data to a single die, you could go down to, say, an OP of 5% and be at a lower overall WAF of 2.2. Or you could come down to close to 1 with that original 25% OP and translate that into other benefits. Now, it doesn't come for free, right? Because on the right-hand side, obviously, if you're not striping across the entire drive, the performance also goes down commensurate with how wide you're striping data. And so, but we do think this is a fundamental tool, and it's something the application should be able to make decisions and be able to control this trade-off. So just to make it a little bit more concrete, in SmartFTL, what happens during a write? So you've got an application. It's linked against this SmartFTL library that showed up in the stack pictures earlier on. and the library sort of abstracts this a little bit for the drive. So the application starts up and creates a number of write objects with the library, and these write objects have are configured with different stripe widths, right? So effectively, the application's expressing its performance requirements to the library. So if I've got, if I have a certain subset of the data that doesn't need the same read-write performance characteristics, I can stripe more narrowly and get garbage collection and WAF benefits. So the library, so the application would group data based on its performance and its expected lifetime characteristics and write those through the various write objects. And then down in the SmartFTL library, it translates that into just normal NVMe writes, sends it down through SPDK, tags them with the correct die and append points within the die. Yeah. So then, if you build on top of that the host GC mode, this is sort of an additive capability. In the pure normal write path, the positioning mode functionality is still active here. What's added is essentially a very simple starting garbage collection state machine. It's kind of uplifted from the drive. So you have essentially a check for a garbage collection credit, and then the host library maintains a mapping table and keeps track of occupancy and does garbage collection ahead of the drives need to do that. And it can make, so the benefit here is the library can make up calls and do tight integration with the application for selecting GC candidates. It can also coordinate when the garbage collection happens. So if the application has lulls where it can make some forward progress, it can be done ahead of time. I will say that we see that just pure positioning mode without the host GC functionality is one of the core benefits. The observation is that if you're going to get to a WAF of 1.0, you're going to do it entirely with initial layout and placement. You're not going to, by the time you've done garbage collection, you've obviously incurred some overhead, and so you're never going to get to WAF 1.0 with garbage collection improvements. But this has a lot of potential for tight integration with application, and for those cases where you really have a hard time getting down to low write amplification numbers. Just going back to the RAID thing I said earlier. So one critical element of SmartFTL is that an underlying RAID layout really isn't compatible with this. With a RAID setup, normally you go across dies so that correlated failures, you'd be insulated from die level or block level read error correlated events. And that sort of forces you into placing parity as you go, which means that when you're given data from the host, there's really no control over where it's placed. You have, or very little. You have to kind of go sequentially, get a parity page out there, and then you can move on to the next kind of stripe down. So one key enabling thing that we see with SmartFTL is that we don't have this need for RAID in these use cases. There is error correction at higher levels, and so this is absolutely something that we're intentionally leaving out from the requirements for SmartFTL. So we see, we sort of see this SmartFTL functionality being useful if your workload has erasure coding at a higher level, or some error correction code at a higher level. If you've got useful data lifetime sizes of between 16K and a gigabyte, much bigger than that, and you're not really taking advantage of the stripe width, sub drive level stripe width capability, and you have some flexibility on sequential read performance in the 64K to 100 megabyte object read size, and we do think a cluster file system workload is a good match for these characteristics. Smarty, if you wanted. I think Smarty's going to wrap up here. So.
Yeah. So I think the net of this is we are here today because we want to actually share this concept with all of you and get your feedback, right? We want to see, what do you think of this SmartFTL concept? Do you see the similar gap in your use cases? Is it useful to you? Earlier on, there was another talk where they talked about the objective, and I think we all share the same objective here, is we want to work with the hyperscalers, OEMs, and the community and the suppliers to come to a common ground here and see if this can be useful. So we want to standardize and enable this concept adoption. We are co-developing with our suppliers like Samsung, Kioxia, and Intel. And we have a library which we think we can open source once we have a combined understanding of the spec. We want to drive this towards. So we want to be able to do that. And we want to eventually standardize this through NVMe. And we are here at OCP because we want to start engaging in the OCP storage groups and see if the specs could be evolved to include this as well. So we look forward to, please reach out to us, whether here we can share our emails. We'd love to hear feedback, and we look forward to participating with the OCP community. Thank you.
And yeah, we can definitely questions.
Hi. You keep mentioning application all the way through, but is the complexity of this isolated to this cluster file system layer? And the ultimate applications, your first slide there with all the Google apps, they just deal with the cluster file system. They don't have to know about the SmartFTL. Is that right?
Yeah, I think the case we're worried about here is the cluster file system case, and it's all within the lower layers of the file system that we're working on this functionality. And
that isolates it from your.
Yeah.
So when you say application, it really only goes up to that level.
Right.
All right.
Yep.
Thank you.
Yep.
I think maybe to add to that, I think maybe there is a little bit of a there's knowledge of which application, right, that you're talking, the endpoint, so it can differentiate at the application level as well, but yeah.
And if you saw earlier in the presentation, there are two modes, right? There's the positioning mode and the host
GC mode.
Host
yeah.
GC mode. So it is to actually accommodate different applications we have. Any other questions?
There's theoretically some way to have online questions, or nothing? Okay.
Everybody's got, oh.
Okay, we have one brave person asking.
Yeah, so what's the complexity of the application? And you basically mentioned that application has to choose, and you also mentioned that it goes down to the die level. So imagine in a cluster file system, you may be upgrading your drives at some point of time as well. And how is the information that the application provides passed along, and what's the complexity there?
I think an upgrade on a drive level is a migration of data or a movement of data, right? So it's essentially getting rewritten somewhere else, right? Or you're augmenting space. So I think. So I'm trying to understand the detail of the question.
It could be basically what I'm trying to say is that there could be you may add more capacity to your cluster file system at some point of time, and so you may not have the same number of dies. Is that a problem? Because my concern is that what should the application know? Should the application know about the drives, or does it know about how it's going to read and write the data?
Yeah, I think this question gets back to the first one, and we probably are, from our perspective, we're working pretty low down the stack at Google. Application is above us, right? And really we're working within the cluster file system layer. So, and all of what you're talking about in terms of die level control is really down at the drive, is managed at the drive level, right? And so that's all. The applications are insulated from that. So I think I don't know if that answers your question or not, but.
Okay, I think I understand it. It's a cluster file system that handles this thing and not the real application itself.
Right, so essentially the contract is the cluster file system is making performance guarantees for an application, right? And it's using these tools to manage that in combination with other ones that are available in the cluster file system. But.
I have a question. So there's an architecture called Open SSD, is this something similar to that?
Architecture group, sorry, could you repeat that?
Called Open SSD, where the host manages a lot of the functions.
Is this like open channel?
Open channel, you mean?
Yeah,
Open
yeah,
channel
yeah.
SSD.
So I think open channel is something we looked at along the way in the development of this, and I think we saw kind of a lot of limitations imposed by that on the drive in terms of NAND management or suboptimal, not optimal cases. Also, I think so. The short answer is it's fairly different than that in intentional ways, based on the trends we sort of were relaying early in the presentation here in terms of offloading functionality and, for example, an open channel, open SSD drive, you've got to full-time take the responsibility of that mapping DRAM on the host, and you have to do garbage collection decisions there, whereas in pure positioning mode here, you don't have to take any garbage collection responsibility on the host. You just have to tag writes as they go by, so it's very low overhead. So the impact in terms of CPU cycles to implement would be considerably lower than something like an open channel or kind of open SSD kind of architecture. I think that was one of our other points. Smriti was mentioning our early drives had almost all the functionality on the host side, and we sort of started with something that looked like an open channel, open SSD drive, and we sort of have moved away from that over time. So we saw some of that as sort of a regression almost in terms of the functionality that we've evolved to over time. So,
Sure.
Term sometimes used as hyperscaler, sometimes it's called cloud service provider. There's obviously, we all know and love Google Maps, Google Gmail, Google, but at the same time, you guys are also landlords renting to tenants in a cloud service environment. Do you see the SmartFTL with your cluster file system more for your internal applications, or do you ultimately see at some point in time a SmartFTL going all the way to a bare metal, landlord-tenant sort of model?
Yeah, I think I'll repeat what I said. This is focused on the cluster file system workload. I think there have been other talks externally where basically there's parts of cloud services that run on top of our cluster file system, and then there's clearly all these Google services internally that run on top of the cluster file system, both of them. And so being below that layer, it's actually kind of targeting those portions of the workloads that utilize that cluster file system piece.
So if you were to bare metal or something like that, would it talk directly to SmartFTL protocols, do you think, or is that?
I mean,
is that something?
Okay, I think there's a level of subtlety there that it may or may not. But I think the way you think of bare metal normally, where you're talking to a physical drive, like this wouldn't be something that would be in the picture in that case.
And that is why we have both the modes, right? We talked about the positioning mode and the host GC mode. It is because other applications may require the regular mode, right, as opposed to this positioning mode.
Thank you.
Yeah. Any other questions?
So I think, like Smriti said, we're planning to get more involved with the storage working group, and so hopefully we'll see some of you in those meetings, or
And get your feedback and
yes.
evolve the spec here.
Yes.
So thank you, everyone.
Thank you.